So for questions like this that you're going to see on the Postlab, we're assuming this kind of reaction's going on here. HA is dissociating at least a little bit into H plus and A minus. And setting this up as we would in class, we have initial molarity and then we'll have equilibrium molarity. Now initially all we're going to have is HA, which is going to have the concentration listed in the question, which is 0.20 molar. But initially there won't be any H plus or A minus present. At equilibrium, some of the HA will split apart into to H plus and A minus, but the amounts of each will be the same. And then we're going to lose that exact same amount from the HA. Now the reasoning behind this is that initially all we've got is HA. So let's say I have, say, 3 in there. And then one of them splits apart at equilibrium, so this will be initial. This will be equilibrium. We'll split 1 into H plus and A minus, and it should be clear to you here that we lose as many HAs as we gain H plus and A minus, but the amount of H plus and A minus are going to be the same. So I'm just calling that Z right there. So in order to calculate the concentration of H plus here, which is going to be Z, by the way, then we can use the pH that's given in the question. Now the pH is 1.42, and we're assuming that that's at equilibrium. What we know is that pH is equal to the negative log of the hydrogen ion concentration, negative log of H plus. So in order to get the concentration of H plus, we would do 10 to the negative pH, which in this case would be 10 to the negative 1.42. And we're instructed to just use decimals here, so we will, and it's going to end up being, in this case, 0.0380 molar. So that'd be the answer there. Now the concentration of A minus, as you can see here, is going to be the same. So the amount of H plus the amount of H minus, is going to be the same. So it's going to be 0.0380 molar. So no difference there. Now the amount of HA, as you can see, is going to be 0.20 minus Z, which is of course the hydrogen ion concentration. So it's 0.20 minus 0.0380. And if we take into account significant figures, the fact that there's 2 places past the decimal here, and then 4 places past the decimal here, our answer comes out to 2 places past the decimal. So it'll be 0.16 molar once you put that in your calculator and you round it out to 2 decimal places. The Ka is going to be the reactants, the products over the reactants, H plus times A minus over HA. And that's going to be, in this case, 0.0380 squared over 0.16, and that comes out to be 0.00903. Again, try not to use scientific notation for these, because that's what you're directed to do in the question. And the number of sig figs here, we've got, well, it should be actually probably 0.0090. There's no unit on Ka. You could put one if you wanted to, but there's no real need to. In this case there's no unit, and just to make it 0.0090 down to 2 significant figures. Alright, so let's look at the other questions here, questions 6 and 7. So I'll select this and delete it. Now I'm not going to go through the full working on these. I'll just make sure that you understand exactly what's being asked for here in both of these cases. In question 6, this is related to part C of your lab. And question 7 is related to part D. So these are 2 different things that we're doing here. It's important to make sure you read the entire question as well as the hint given here as to which equation to use, and that's really what I want you to focus on here. So for the question 6 here, the situation is that we're preparing a buffer by taking B minus, or we'll say BH over here, and B minus over here, and then adding them together to to form a buffer, which is going to be a mixture of, let's make that a little bit bigger, a mixture of BH and B minus. So that's how we're getting our buffer there in part C. And it's important to note that what we're trying to solve for here is we're using this equation, the one I'm pointing to here, and we're solving for the volume of B minus. Now in the case of part D, it's a bit different. What we're doing is we're taking BH and we're adding in, and I'll put in 4 here. It's just pure BH, that's all we're adding, and I'm going to add in 2 by OH minus to this solution. Now what's going to happen is I'm going to end up getting this, BH, BH, and 2 of the other BHs will convert into B minus and B minus. Now the reaction that's occurring here is that BH plus OH minus gives B minus plus H2O. We're not interested in the water, we already know it's an aqueous solution, but if you look at the end result, it's a buffered solution just like we got for part C here. And it's important there to use this equation, because what we're finding here is that the concentration of B minus is going to be the same it's going to be the same as the, let's do that again, we'll do it with the volumes. The volume of B minus at the end is going to be equal to the volume of OH minus that was added. So that's why if we look at the equation here, we've got the volume of OH minus on top here, whereas over here we have the volume of B minus, but that's going to be the same thing. So volume of OH minus is going to be on top. And you'll notice that the volume of HB now is going to be the initial volume of HB, which in this case was 4, minus the volume of OH minus added. So we lose as many BHs here as we have added OH minuses. So that's why that goes down by that amount. And that's why in this bottom part here, we've got volume of HB minus the volume of OH minus.